In today's presentation, we'll start with a brief recap of containers and containerization. We'll look at exactly what Kubernetes is and how it came about. We'll examine the architecture and some of the more important components that make up a Kubernetes cluster. We'll see how we can run and manage containers in a Kubernetes cluster. We'll examine some of the features that allow us to handle storage, networking, and security in Kubernetes. And we'll take a look at what Kubernetes looks like today and some of the major offerings that exist to help you run Kubernetes in your environments. Now, before we get into the presentation, if you haven't had the chance to catch the last workshop in the DevOps for SysOps series on containers and containerization, I would highly recommend checking it out after this presentation's over. In it, we discuss the basics of what a container is, how we can use container engines like Docker to create and leverage them. I'll paste a link to that in the chat right now. Now, to quickly recap what we learned in the last presentation about containers and their benefits, we learned that containers are lightweight packages of code. The dependencies the code needs to run, and just enough operating system for that code to run. We saw that with containers, they are lightweight enough to where we can simply create new ones if the old containers are crashing. And we're no longer focused on maintaining a whole operating system. We're just focused on the application. We saw that since all containers are sharing the host operating system kernel and nothing more, they will run the same across any environment. And we saw that if we use containers to build microservice-based applications, it's easy to scale, upgrade, and roll back individual components of our applications with minimal downtime and rapid speed. But at the end of the last presentation, we saw that managing a fleet of hundreds of containers could prove challenging. With virtual machines as our container hosts, how would we manage containers across all of our virtual machines? And in increasingly complex environments with multiple VM hosts or even cloud infrastructure added to the mix, how would we manage all of our containers? Managing them on each machine individually, one by one, makes no sense. We need to manage the entire fleet of containers across our entire infrastructure. And like I said at the last presentation, that is where Kubernetes comes in. So what exactly is Kubernetes? Kubernetes, simply put, is a container orchestration platform. It's a platform designed to automate the deployment, scaling, and management of containerized applications across multiple hosts. If a development team decides to containerize one of their monolithic applications, Kubernetes provides the infrastructure to manage and scale that application. So the platform was developed by Google originally in 2014 as a solution to their own container management problem. And in 2015, Google partnered with the Linux Foundation and formed the Cloud Native Computing Foundation to make Kubernetes an official open source project. In 2018, the CNCF declared Kubernetes a mature and stable technology that could be used in enterprise. Today, there's support to run Kubernetes pretty much anywhere, and it's fast becoming the backbone of infrastructure for all sorts of modern applications, especially AI applications. Now, before we continue, I just want to point out that when you look at the word Kubernetes, there are 8 letters between the K and the S, which is why you may see some people refer to Kubernetes as K8 or Kates. Just a little tidbit before we continue. So why do we run Kubernetes? Why has this open source project gained so much traction and adoption over the past few years? First off, Kubernetes allows us to have all the benefits of containers and containerization, but at an enterprise scale. Across our infrastructure, we'll see that we can achieve operating system independence, rapid development and deployment, and environmental consistency. And with Kubernetes, we can manage our containers across our infrastructure with Kubernetes as the single pane of glass. We don't need to manage each container host individually. We can oversee our applications across all of our machines. Kubernetes is constantly evolving and adapting with new trends and technologies thanks to the contributions of the open source community. As of June 10th this year, there were 63,495 contributions to the open source project from 318 companies alone. And since this community is overseen by the Cloud Native Computing Foundation, it is evolving in a direction that's steered by the best interests of the industry, with companies like Google, AWS, VMware, and Red Hat all sitting on the CNCF board. And arguably the best feature, Kubernetes gives you the freedom to run anywhere. If we spin up Kubernetes on one platform and want to move to another platform, we have the ability to migrate easily and quickly. If we wanted to, we can move our clusters from AWS to VMware, or even vice versa. And we can even run clusters across multiple platforms if we wanted to. So how does Kubernetes work? Before we look at running containers in Kubernetes, let's look at what makes up a Kubernetes cluster. In Kubernetes, a cluster is the set of machines or nodes that are connected together to run your applications. Think of it as a large set of connected Docker hosts, or in terms of virtualization, a cluster of ESXi or AHV hosts. Now, in a Kubernetes cluster, there are two distinct categories of nodes. You have your control plane that will handle the management and maintenance of your cluster, and the worker nodes that will actually host and run your containers. Now, in the control plane, there are four key components deployed by Kubernetes that allow for container orchestration and management. The first, and arguably the most important, is the Kube API server. Now, the Kube API server acts as the central point of contact for all communication in a Kubernetes cluster. Any actions taken by us through the command line are sent directly to the API server, and all communication between nodes will traverse through it. The second component is the etcd server. This controls and manages the cluster's etcd file. Now, the etcd file is the configuration file for the cluster, or the source of truth for how the cluster should look. Now, the third component is the scheduler. The scheduler is the component of the control plane that selects where newly created containers will run. Utilizing information from the worker nodes, the scheduler will handle the logic of deciding the best worker node to place your containers on. And the fourth and last component of the control plane is the controller manager. Now, controllers in Kubernetes will monitor and manage the different objects we spin up in our cluster. An example controller is the node controller, which monitors node health and handles remediation if a server suddenly becomes unreachable. Now, there are many other controllers baked into the controller manager, and we'll see a few in today's presentation as we go along. Now, a key component deployed on not just the control plane, but every node in your cluster is the kubelet. Now, the kubelet is the agent that ensures that containers are running in your cluster, and it reports back to the API server for the health and status of all workloads running on its given node. A good way to think about this is if the Kube API server is the regional manager of your cluster, then the kubelets are the on-site managers that report back to it. And as said before, all workloads that are deployed and managed through Kubernetes will run in your worker plane. So now that we have a good idea on the architecture of a Kubernetes cluster, let's look at how we can actually run our containers inside of it. Now, let's say we wanted to spin up a web server container, and instead of running Apache, we decided that we wanted to use Nginx because we heard it works really well in Kubernetes. It does. Now, to run this container inside our Kubernetes cluster, we need to package it into a pod. Pods in Kubernetes are the smallest deployable unit of computing that you can create and manage in Kubernetes. We can think of a pod as a wrapper around a container. And Kubernetes will manage the pod rather than managing the container directly. If we wanted to, we could even create a pod with multiple containers inside of it. Let's say that we wanted to deploy a lightweight logging container to pair with our Nginx container. Now in our pod, we would specify our Nginx container, and our logging container as well. And the two containers would form one cohesive unit, sharing the same resources. But for now, let's just focus on a single Nginx container running in our pod. Now, to create our pod, or any object in Kubernetes, as you'll see going forward, we need to create a YAML file. Every object in Kubernetes is expressed as a YAML file to the API server. Now, to create our pod, we need to create one that details the container image we're running and how it should be ran. Now, in every Kubernetes YAML file, there are always 4 sections of information: the API version of the object, the kind of object we're creating, the metadata of the object. This can be just a name or any other labels or annotations we want to put on the object. And most importantly, the spec. This will detail exactly how an object will run inside our Kubernetes cluster. In our case, we're simply specifying we'd like to run a single version 1 Nginx container with no other configuration details on how that container should run. Now, to send this object to the Kube API server, we use the kubectl command line tool. Now, kubectl allows Kubernetes users to interact with the cluster. We can create objects, update them, delete them, and even manage the cluster using this tool. And once the API server receives the request, the scheduler will decide which node that the pod will run on, and the kubelet on the chosen node will spin up the pod. Kubectl also gives us the option to bypass creating YAML files manually. Using the new kubectl run command at the bottom of the screen, we can specify the name and the image of our pod, and our YAML file will be generated and sent to the API server without us having to type it out ourselves. This option is great for quick pod creation, but creating YAML files ourselves allows us more options for customizing the configuration of our pods. Now, we know that it's neither smart nor efficient to run our application on a single container. And while we can have multiple containers inside a single pod, in Kubernetes, it's best practice to split up our microservices into separate pods. So how do we deploy multiple pods efficiently? One by one would work, but that's so tedious. Luckily for us, Kubernetes makes it easy with ReplicaSets. Now, ReplicaSets are sets of identical pods that can be scaled up and down to meet our demands. For our Nginx pod, we can turn it into a scalable replica set by utilizing the YAML on the right. And if we look closely, we can see that we're defining the same pod spec as before and the number of replicas of that pod that we want spun up. In our instance, 3. Now, replica sets are managed by the replica controller, which is a part of the controller manager in the control plane. The replica controller will monitor our replica set and ensure that the desired number of pods are running and healthy. Now, let's say that we know traffic to our web server is about to increase, and we need more instances of our Nginx pod to keep up. Using the kubectl tool, we can scale up our Nginx replica set from 3 instances to 6. Now, the replica controller would see this change and spin up 3 more pods. Now, after this traffic spike to free up compute resources, we can use the same command to scale back down to 3 replicas. And the replica controller would remove 3 pods from our replica set. And for some reason, if one of our Nginx pods were to crash, the replica controller would see this, remove the unhealthy pod, and spin up a new one. Now, replica sets are great for scaling our applications, but in order to manage the entire lifecycle of our application, we need to create deployments. Now, as we can see, when we spin up a deployment, we're actually spinning up a replica set that's now under the management of a deployment. But now, with deployments, we have access to rollout, upgrade, and rollback strategies that allow us to operate and maintain our applications with near zero downtime. How does this work? In our new deployment YAML on the right, we can see that it's pretty similar to the replica set YAML from earlier. But a new field named strategy has been added. Here we can take advantage of the rolling update feature within Kubernetes deployments. Let's see how a rolling update looks like in practice. Say we wanted to update our Nginx deployment to use a newer image. Using the kubectl set image command, we can upgrade our deployment from version 1.0.0 to version 1.2.0. Once we send this command to our API server, a second replica set will be created for our upgraded pods. And as the new pods are spun up in the new replica set, old pods are deleted from the old replica set until the new replica set is fully populated and the old replica set is empty. And another great feature of deployments is that a history is kept of each version of our deployment. So in our instance, let's say that version 1.2.0 is full of bugs and we need to go back to the old version of Nginx ASAP. We can use the kubectl rollout undo command and specify the version that we want to roll back to. And the rollback will function the same way as the upgrade, one pod at a time from each replica set until the original deployment is restored. So now that we have a good idea on how we can run our containers in a Kubernetes cluster, let's look at some of the features that make Kubernetes so powerful at scale. For now, let's focus on our 3-pod Nginx deployment running in our worker plane, with 1 pod on each worker node. Now, on our web server, we need to give these pods access to a number of files and pictures for our website to display. Now, to help with this, we can leverage a familiar feature from containerization and Docker, persistent volumes. Now, to recap persistent volumes, they are storage volumes that exist independently from any pod that accesses its data. No matter how many pods we spin up or tear down, it doesn't affect the volume unless we want it to. Pods can both access and, if we want to, write data to our volumes. If a pod makes a change to a persistent volume, those changes will persist even if the pod is no longer running. And finally, as I've mentioned before, our persistent volumes will not be affected by any changes to our environment. All changes to our persistent volumes must be done manually or be triggered by a container that a user spins up. Now, our persistent volumes in Kubernetes can be blocks of storage on our worker nodes, or they can even point to external storage that lives outside of the cluster. Now, in this example, let's say our persistent volume is located directly on worker 2. And now, in order for our pods to be able to access the persistent volume, we need to create a persistent volume claim that is mapped to the persistent volume. Now, while persistent volume claims and persistent volumes will always have a one-to-one mapping, all the pods in our deployment will be able to access and mount the same persistent volume claim. If we take a look at the YAML of our persistent volume from the example, as well as the YAML of our persistent volume claim, we can see that our persistent volume claim in the middle is mapped to the persistent volume on the left. And if we look at the updated pod spec of our Nginx pod, we can now see that it's referencing the persistent volume claim and mounting it to the container's own file system. Now, to clarify, in our diagram, we have an Nginx deployment, but for simplicity's sake, I wanted to show how a singular pod mounts a persistent volume claim. Now, for some cases, we don't need to create storage volumes to host the data our pods will need access to. In our example, each of these Nginx pods are going to need to access an Nginx configuration file. Now, while we could bake this file into our pod spec or store it in a persistent volume, a better option would be to create a config map. A config map is a lightweight Kubernetes object that's meant to store configuration data. In our case, we can create a config map from our Nginx configuration file, which can then be accessed by all of the pods in our Nginx deployment. If we look at the YAML for that config map, we can see that under data, we have one variable listed, and it's the configuration file for our Nginx pods. Utilizing this strategy, if we need to make changes to this file, We can change them here and simply redeploy our deployment to update the pods to the new configuration file. And we can also store sensitive configuration data, such as credentials or API keys, in a similar fashion, using Kubernetes secrets. With secrets, the data we store inside them is base64 encoded and can be loaded into our pods the same way as a config map. Now, base64 encoding is good, but in order to keep our secrets safe, we can utilize third-party secret managers, such as HashiCorp Vault, to securely store our secrets and the data inside them. So, just to quickly recap the storage capabilities of Kubernetes and the best use cases for the objects we covered, we can leverage persistent volumes and persistent volume claims to give our pods and deployments access to readable and writable storage volumes. We can use config maps to store configuration data and other small variables our workloads may need, and secrets to provide an added layer of obfuscation to our sensitive information. Now, moving on from storage, let's talk networking. How do we give the pods in our cluster the ability to communicate with each other? And how do we get our users the ability to connect to our pods? The good news is when we deploy Kubernetes, we deploy an internal pod network for pod-to-pod communication. This is possible thanks to container networking interfaces, or CNIs. Some popular and free and open source CNI plugins are Cilium, Calico, and Flannel. And the great part about these CNIs is all you have to do is install the programs onto your nodes, and Kubernetes will take care of the rest. And another great feature of Kubernetes is that core DNS is installed by default, which acts as the DNS server for the cluster, giving every pod its own service name. Now, although a CNI and core DNS helps with giving our pods the ability to network, giving each pod its own IP and hostname, the problem with Kubernetes is that we're constantly spinning up new pods and tearing them down. This means that the pods in our cluster will constantly be assigned new IP addresses, new DNS hostnames, making networking a challenge at scale. Luckily, Kubernetes offers a feature called services that allow us to create stable endpoints for our pods and deployments, and we can use those services to enable stable communication. This way, when we need to communicate with a pod or a deployment, we can direct traffic towards the service, which will then route the traffic towards the appropriate pod. So, how do services work? Let's say we want to get external users access to our Nginx web server, but with our deployment constantly being scaled and updated, we need to create a stable endpoint that these users can connect to. This is where node port services come in. Node port services are pretty self-explanatory, and we are exposing a port on our nodes. But in this case, we're mapping the port on our containers to the port on our worker nodes. So when a user wants to access our web server, they can connect to the open port on our worker node, which is mapped to a pod in our deployment. Now, node port services are great for enabling external network traffic, but how do we handle internal traffic between the resources in our cluster? Let's say that we created another deployment to interact with our Nginx deployment. In this case, we launched a deployment of pods that run a Python script, and we want the script's results displayed on our web server. Now, to ensure stable communication between these deployments, we would create a cluster IP service for our web deployment. Now, a cluster IP service, much like a node port service, creates a stable endpoint for our Nginx deployment. But in this case, it's strictly for internal pod-to-pod communication. How it works is when a pod from our Python deployment needs to communicate with the Nginx deployment, traffic will be sent to our new cluster IP service. And the service will load balance our traffic and decide which pod the Nginx deployment needs to send the traffic to. And no matter how many pods we spin up or tear down, the service will stay persistent, allowing for an ever stable communication. Now, to recap services, we can utilize node port services to expose our pods and deployments to external traffic with a stable endpoint. And we can use cluster IP services for stable pod-to-pod communication. Now, by this point, we can see that in a Kubernetes application, there are many components that work together. If we decided to incorporate our web server into a 3-tier application, like we did in the last presentation, we would have individual pods, deployments, storage, data injection solutions, services for networking, and a slew of other objects that we aren't even covering today. Luckily, there's an open source tool in Kubernetes that allow us to package together all the components of our microservice applications for simplified deployments and maintenance. And that tool is Helm. Helm is the official package manager for Kubernetes clusters. As I said before, all microservices that make up our applications can be packaged together using Helm to simplify rollout, upgrade, and rollback strategies. It's an open source project, and it's even managed by the Cloud Native Computing Foundation, the same organization that oversees Kubernetes. And no matter where you're running Kubernetes, Helm can be ran with it. Now, how Helm works is we can take the manifests or the YAML files of all of our individual components and package them into what's called a Helm chart. Now, there are many public Helm charts available on the official Helm repository for public applications, but we can also create our own Helm charts with our own Kubernetes YAML files, packaging all the microservices and features that make our application. Now, to deploy a Helm chart into your Kubernetes cluster, you can run the Helm install command with the location of your Helm chart, and all the components that make up your application will be deployed into the cluster. And like deployments, Helm keeps a history of chart versions and rollouts, so rollback strategies are available and easy. Now, looking at the state of Kubernetes today, it's come a long way since Google pushed its first release more than a decade ago. While it can be deployed as a standalone technology that we can manage, managed Kubernetes offerings span across any infrastructure you'd like to run it on. For cloud offerings, AWS offers EKS, Azure with AKS, and Google with GKE. And while these cloud offerings are great, on-prem offerings from hypervisor companies have made leaps and bounds over the past few years. VMware has made significant improvements to their Kubernetes platform, VKS, Nutanix with NKP, and Red Hat OpenShift, and Rancher if you're looking for a more dedicated Kubernetes solution. And the best thing about all these platforms, as well as over 60 other verified platforms, is that they're all running Cloud Native Computing Foundation compliant Kubernetes, which means every platform is running the same exact thing. No matter where you choose to run your containers, they'll run the same across any of these Kubernetes platforms and be managed in the same way thanks to Cloud Native Computing Foundation standardization. And if you want to migrate between the platforms or even run clusters across multiple platforms, you have the ability to do so.